professor at University of Maryland since 2001. And so Mike has done a lot of work. I think he has worked on programming languages, systems, mostly on software security and reliability. I think he's best known for his work on dynamic software updating and Cyclone. And more recently, he's moving to some new areas to do with cryptography and programming languages, also quantum computing, and as well fuzzing and probabilistic programming. So Mike just finished his service as a 3-year as a chair for SIG Plan, and Mike also won many awards. One, I think, notable ones, including SIG Plan Outstanding Dissertation Award, and also a NSF Career Award, and many other awards. Okay, so with that, let's hear from Mike.
Can you, there, yes, you can. Thank you for that nice introduction. I'm very happy to be here. So that's me. I'm the one giving the talk, but I want to emphasize that of all of these co-authors, the first author, who was my postdoc for 2 years, was the main driver of this work. He's now a professor at UT Dallas. So the topic of my talk is what we call numeric static analysis, and we're focusing on Java programs. And the idea with this sort of analysis is to prove numeric properties about programs. So for example, we might want to prove that an index to an array is always in bounds. An index is a number, so that's a property of reasoning about the manipulation of that number inside of your program. You might like to prove you never divide by 0. You might like to use numeric analysis to prove properties about running times, to say, for example, that running times don't differ when you bury secrets in your program, and therefore that you don't have any side channels. So this, in fact, was the motivation of the development of the analyzer that I'm going to talk about today. So oftentimes, numeric static analysis is phrased as an abstract interpretation. And so that's sort of the way that the paper presents this work. I won't end up talking about it too much in those terms in this talk, but if you do go look at the paper, you'll see that. And the challenge that we faced for the work we were trying to do was to make an analyzer that worked for full Java programs. So we wanted it to be mostly sound, so we could try to make strong statements about not having side channels, for example, but then also work for large programs and still be precise. So in looking through the literature to try to understand how to build such a tool, we found that there really was no prior work that handles the heap, method calls, and numeric domains all together in a way that scales and requires little human work. Now there's many design choices and many bits of work that operate in parts of this space, but most of these explain their techniques in sort of a folklore style. That is, they'll assert that something is true, they'll compare against something that's slightly different than what they did. It'll seem that what they did is definitely better than what was slightly different. But the whole big space of all of the ideas in static analysis, which ones are the best ones to put together, and what are the trade-offs of the different approaches, that's harder to say. Mostly papers would consider just these single choices, for example, whether a precise numeric domain is too much slower than a less precise one for some certain application. So this is just sort of a list of all of that work. I'm going to skip past it, but none of it really reached the goal that we were interested in. So we set out to build our own static analyzer for Java programs, and when we realized that the prior work was not pointing us in the completely right direction, we decided we needed to do a little science to figure out what set of analysis options might make sense. So we actually ended up implementing an analyzer that works for many configurations of different options. We looked at different so-called numeric domains, different ways of considering the heap, different ways of representing objects in the heap, different abstractions, how to analyze different methods, and levels of context sensitivity when analyzing those different methods. And we looked at how each of those options traded off with one another in a set of benchmarks. So in particular, we looked at the DaCapo benchmark suite with our implementation, and we measured how well it did in proving array indexes were in bounds to see what these different analysis options contributed to and against that goal. The way that we went about doing this, it turns out that it's hard to understand data that involves 162 different configurations. If you just look at all the data, how do you identify reliable trends? So what we did was we did a multiple linear regression where we did basically a statistical analysis to try to match the different configuration options against the actual performance that we saw. So the programs in this linear regression are independent variables, and so are the analysis options. So all of those things are basically, we're trying to predict precision and performance as a function of these independent variables, of the choices you make and which heap abstraction you use, which numeric domain you use, and so on. And then we also have the programs as providing their own program-specific features so that we could ignore those and focus on the things that were common across all programs. Assuming that we have a good model fit, which it turns out we did, this would help us understand. We don't expect that performance is literally going to be a linear function of these things, but it might give us some insight as to which options have the most impact for both precision and performance. We also did a bunch of visualizations to try to plot the different trade-offs between precision and performance to see where the sweet spots might be. So our results, I think, clarify a bunch of trade-offs that hopefully are not surprising, but maybe are more useful because they don't say just, for example, that convex polyhedra, a well-known precise numeric domain, is more precise than intervals and less efficient. It says how much more precise and how much more efficient, especially when coupled with many other features that are going to be involved in your analysis. And so then these trade-offs give you some sense of how you might want to build your own analysis depending on the features of your benchmarks, of the programs you care about. I would say in general that what we discovered in doing all of this work is that there's a lot of information that doesn't make it into the paper. That whenever you build some tool, there's lots of engineering that happens that somehow escapes notice in the write-up. It's just about some idea that's focused on in the paper, and lots of other details that made that idea possible don't get talked about, so that if someone comes later to try to reproduce your work, they can't do it. Or if the setting is slightly different and the results are not the same, they're not sure exactly why. So I would say that it would be great to move past such a dogged focus on novelty, do I have a new feature, but to also just appreciate empirical work. If you just take the same analysis that someone did before and apply it to a totally different benchmark suite and look at different trade-off options, this would be really valuable, and yet it's something our community, the PL community and the software engineering community, I think, don't appreciate as much as they could. And who knows, maybe this way of the research that we did it might provide a template for others as well. So all I'm talking about is in this paper that's on arXiv. It's a longer version of a paper we had at ESOP this year, and the code for our analyzer is also free online. Okay, so here's all of the analysis configuration options. I'm going to go through each one of these groupings. There's 5 groupings, and we'll take them one at a time. So first, let's talk about the numeric domain. The numeric domain is the part that makes it a numeric static analysis. It's reasoning about the manipulation of integers in particular in your program. So here we have a little program on the left, and during our analysis, our abstract interpretation of this program, we might know at this particular line that x is equal to 1, and then at this next line, y is equal to 1 because x was 1, and so now y is 1. And that's going to allow us to assert that y is equal to 1 here. Now, on the other hand, if we have this program where we don't know what x is, and we set y is equal to x, at this program point, we're going to say that y is equal to top, right? We're just going to take whatever x was and assign it to y, and because we don't know what x is, because it was the console input, top, we don't know what y is, and when we assert that y is equal to x, we're going to get a false alarm. It's going to say, no, that's not true, because y is top. Now, if you use a relational domain, like convex polyhedra, you're going to say x is equal to top, but here you're going to say y is equal to x. You'll keep this equality inside of your analysis domain, so you know the relationships between the variables, and then you'll be able to make this assertion. So this is a well-studied area of program analysis and abstract interpretation using so-called convex polyhedra to keep track of these per-variable relationships. Now, it's well known that doing that is far more expensive than intervals, than the thing that was on the left-hand side. And so there's a trade-off here that you can prove more things with convex polyhedra, but it takes a lot more time and may not scale. So that's the trade-off that we have to look at for our set of applications. Okay, so programs don't just have variables that store numbers in them. Java programs have the heap. And in fact, most of a Java program is stuff that's stored on the heap. So we need some way of analyzing the heap if we're going to analyze Java programs. A key ingredient to heap analysis is a points-to analysis. And so points-to analysis considers aliasing relationships amongst different pointer variables, reference variables in your program. And aliasing matters because if I assign to x.f, that may affect other variables in my program, for example, y.f, if x and y are aliases. So a simple way of thinking about what a points-to analysis is it's an analysis that produces a map from program paths, like x.f, to a set of abstract locations, where a path is either a variable z or it's an access path, path.f. And the abstract locations are just some way of describing one or more locations at runtime that represent those things for your static analysis. Therefore, if the points-to map for P and Q don't overlap, then that means that they don't alias. So using this points-to map, we can define a heap abstraction to integrate with our numeric domains. So one way to do this is to use what's called an access path, and that's to treat x.f as itself a variable, just like the x and y that we saw in the numeric analysis before. The benefit of this is you can do strong updates. So when we overwrite x or y, we're able to replace the analysis abstraction of x and y. That's a good thing. And you would weekly update those paths that may alias with your access path. So just to explain this terminology, strong update, you can see here on the left-hand side, x is 1, and then when we do x equal to 2, we overwrite the abstraction of x so that now it's equal to 2. That's a strong update. Whereas on the right here, when we assign 2 to x, we abstract x as being between 1 and 2. So this is an over-approximation of the truth. And it's going to be useful for this case where you're approximating what an aliased pointer could point to. So here's an example with access paths. Here's our points-to map. The points-to map is saying that x and w point to this abstract object O, and because they point to the same object, they may alias at runtime. At this point where we assign to x.radius, we can now treat that as a variable, this access path as a variable in our abstract domain, setting it to 1. And then at the next step, when we assign to w.radius, we need to perform a weak update on our abstraction for x.radius because x and w may alias. Right? It means that the assignment, according to this pointer analysis, and also you can see in the actual program, is that w and x may be aliases, and so therefore the assignment of w to w.radius affects x, and so we weekly update it. And then at this point we can set y is equal to 2. Another heap abstraction that's been proposed in the literature is called summary objects, and in this case we have another variable that, in this case we're calling it O.f, that summarizes a set of locations, and we maintain an abstraction about that possible set. In this case, whenever we assign to x.f, we weekly update the path O.f for all O. So this approach both harms and helps precision. It harms precision in that it has no strong updates. We're always weekly updating. However, the global nature of points-to analysis and the global nature of these names that we're producing allows us to consider effects across method calls in a way that access paths do not. And it makes expressible invariance among fields of different objects. If it turns out that your F and G field always had one greater than the other, you could express this using summary objects, but you could not express it using access paths because access paths are purely local representations of what's in an object. Once you assign back to an object or read from it, you're going to lose any global information that you obtain about the object. Now, it turns out summary objects will harm performance because as a global abstraction, you'll end up with many, many more variables than you would with local access paths. And weak updates are also slower than strong updates because you need to compute these joins, this 1 less than or equal to x less than or equal to 2. Computing that weak update takes much more time than overwriting the value of the abstraction for x. Okay, so if we look at that same example, here we have summary objects on the right-hand side, and we can see we have the summary object O.radius that we set to 1. Once we set W.radius, we do a weak update, because both X and W may alias, and so they're given the same abstraction inside of the numeric domain. And here we see that loss of precision. And you can combine both of these things. It certainly makes sense as well to do the thing that we have on the left-hand side with access paths, but then also to, in parallel, have a summary object representation so we sort of get the best of both worlds in terms of precision. We're able to fully track local relationships with strong updates, but we can also capture global relationships using summary objects. Okay, so there's sort of, you can go either way with precision for this particular abstraction, but access paths are definitely more efficient on their face. Okay, so there's also the third trade-off, which is the abstract object representation. So I was showing you that little O there as a way of representing things in the points to analysis. There are different ways that we could represent things. So, for example, we could define that set of abstract locations as tantamount to their locations in the program, where those objects are allocated. So this is the so-called allocation site based approach. So here we have two different allocations of the circle object, and therefore they get two different abstract locations in our points to map. Because they have two different abstract locations, we can see from this points to analysis that X and W do not alias because they point to two distinct abstract objects. Now we could also use a so-called class-based abstract object representation where you have one abstract object to represent all objects of the same class at runtime. So this program would then have this points to analysis in that case. So you can see this is going to be more efficient. We have fewer abstract objects to keep track of, but it's also less precise because now it's possible, according to this abstraction, that X and W may alias. Of course, that's not true for this actual program, but it's therefore going to be a source of improved performance, but reduced precision in the analysis. So we can see that in this example. If we have X radius, we can assign 1. Here we assign to W radius. In doing that, we have no impact whatsoever on X radius on the left-hand side because according to that abstract object representation, they do not alias. On the right-hand side, they may alias, and so therefore we have to perform that weak update that we saw in the prior example. We also considered what's called in the paper that we took the idea from, the smushed string option, which is basically a class-based representation for string objects, but allocation-based approach for everywhere else. It turns out that programs that use a lot of strings are not benefited by distinguishing those strings as different abstract objects, and so it makes sense to collapse them into a single object and therefore improve your performance with very little impact on your precision. Okay, yes?
Why would that matter? Strings are immutable, right? To be fair. Why would one want to separate?
Right, you don't. So that's why this smush string option is a good idea. Okay, so the next one is context sensitivity. This is a way of handling method calls. So I haven't talked about method calls so far. So here I've labeled the two allocation sites for strings, but I've also put labels in front of these two calls to bar. This method down here at the bottom where we pass a string object to it, perform a little work on it, and then return back. So the idea of context sensitivity is to treat different call sites distinctly when you're performing your analysis. And this could happen both in the points to analysis and also in the numeric component that happens afterwards. So here I'm just looking at the points to component. What this is showing is that we'll have two different abstract objects for X and Z. And according to a context-sensitive treatment, when we get inside of the analysis of this bar method, what we're going to do is we're going to say that P could point to either L1 or L2. But in fact, within the call at site L3, we know that X is always going to point to the one allocated at L1, and we know that P is going to point to the one allocated at L2 for the call at L4. So a context-insensitive treatment, when analyzing bar, conflates those two calls together and says that P could point to either one of those two things. Now, on the other hand, a call site sensitive treatment would have two different considerations of this method, one when it's called at site L3 and one when it's called at site L4, and give those two different names in the analysis so that I could distinguish them when performing that analysis. So this is going to this use of the points to analysis this way, if it's context sensitive, is going to lead to a potentially more precise call graph, because in an object-oriented program, what you call depends on what you alias. If P points to this object versus that object, and each of those has a different class, when I call a method on P, I may go to different methods, and therefore it may affect the precision of when I make a call, which method am I actually going to. And it also affects the precision of the numeric analysis, depending on when I get around to analyzing this method bar, what is the abstraction that I use inside of that method. So as you might expect, context sensitivity oftentimes adds extra performance costs because you're increasing the size of your abstraction, you have to do more work, and it improves precision at the same time. There's also a sort of a middle ground type sensitive analysis that we consider between call site sensitive and context insensitive. Okay, so the last trade-off, the last parameter is how do we analyze methods? So one way is to do them top-down. You start from analyzing the main method in your program and you just work your way down, analyzing each method as it's called, using this call graph that you produced. This is going to give you a precise analysis of each call because each time I get to a different call, I'm going to have different information that might allow me to treat that call site distinctly. This is going to be boosted by context sensitivity. If in that call site, if I would sort of travel into the method each time and I have a context-sensitive pointer analysis when I do so, the analysis of that method will have fewer spurious conflations with respect to other calls that occurred in the points to analysis. Now, on the other hand, top-down analysis forces you to analyze the same method multiple times, one for each call, so that's going to take more time. Unless you cache a summary of the method's analysis, keeping track of the abstractions of the arguments that you passed in. And if you, say, in analyzing something in a loop over and over again, realize that I'm calling this method in the same abstract circumstances as I did before, I can remember a summary of that method and just reuse it. And so that's what we did in our particular implementation. So here's an example. I can start at the beginning here, and let's assume that I have a points to analysis that allows me to distinguish x and z. So I've just written that in a different way here on the side. I assign to x, setting its radius to 1. I assign to z, setting its radius to 2 because these two don't alias. And now I go to make this call. So when I get into the call to bar, I can map my access path that I had for x, x.f, down, or x.radius, down to pl3 radius, perform this computation, return the result. It goes back to the call site and life continues, doing the same thing for the other site. Now the flip side is to use a bottom-up analysis, and the idea here is to analyze each method in isolation, trying to compute a summary that can be reinstantiated at each call. The benefit here is you have no reanalysis. You analyze each method once, and then you get to reuse that summary over and over again. This also allows you to be parallelizable, which may be really important for scalability reasons. If you want context sensitivity, you may need multiple summaries so that you can treat each call site independently, or you need some mechanism to describe your specifications for those summaries in a context-sensitive way. So the abstract domain that you use, the numeric domain, is going to matter. Which is to say, you may lose precision based on the summary format. Okay, so here's the top-down one on the left. If we do the bottom-up on the right, what we're going to do is we're going to analyze bar. And in order to analyze bar context-sensitively, we're going to analyze it with two for each of its particular call sites. This is what we do in our implementation. It turns out the summaries are the same for both L3 and L4. Now that I have these summaries, I can now analyze the foo method and do the same thing that I did before. Now when I go to call bar, I can just instantiate the summary by basically substituting x radius for for the first call and substituting z radius for the second call using that summary. Okay, so the idea here is typically we would expect top-down to be more precise and bottom-up to be more efficient, depending on various other analysis options.
What do you do if you don't have any leaves?
What do you do if your entire program is...
If it's mutual recursion.
if you have mutual recursion. So you need a way, so this is a way in which you're not going to be entirely one method at a time. You have to compute a fixed point between these different leaves. So then you'll have some mixture. I guess what we found in the Java programs that we analyzed is that this sort of mutual recursion was uncommon. Okay, so as I said before, all of this code for this tool is up on GitHub. We built our implementation on top of the IBM Walla Java analysis framework. So we use that to parse bytecode into an intermediate representation. And then we used Walla to perform the points-to analysis and call graph construction. For numeric domain backends, we used Apron for intervals, and we used Elena, developed here, thank you, Martin, for convex polyhedra. And our analysis was about 14,000 lines of Scala code on top of all of this other stuff from Walla. So for the experimental evaluation, we considered 3 research questions. One is, how does configuration affect the running time of the analysis? How does it affect precision, where precision is defined in ability to discharge array indexes as being inbounds? And also trade-offs. How does the configuration affect precision as compared to performance? So as I said at the beginning, we use this array index out of bounds analysis as our client, and we analyze it on the DaCapo benchmark suite. So this is a standard Java benchmark suite with programs that are from different domains and vary in size. We looked at these 162 different analysis configurations, and we did 3 runs for each configuration of the program, making sure that the variance that we saw was not too significant. So there was no variance whatsoever for precision, and there was some variance in terms of performance, but not too significant to affect the overall trends that we're looking at here. But see the paper for more details. We used a timeout of 1 hour on each run, and it took about a week to run the whole thing on a single processor machine. So some caveats about these results. If you use a different analysis client than the one we used, maybe you used division by 0 or you computed running times or something like that, it might be that these trade-offs are different. It's hard to say. It may be that 3 trials was not enough. As I was waving my hands about before, most of the performance did not differ by enough that it should affect the trends that I'm going to show you. Our implementation might have bugs. I hope the bugs are not so significant that they completely throw the results off, but it does happen. Okay, so let's look at the data analysis. So as I mentioned at the beginning, we did a multiple linear regression where as the dependent variable, we considered precision and performance. And so our goal here is to say, well, is there a linear function that from all the data that we analyze predicts performance in terms of all of those analysis options and the programs themselves? So those are the configuration options. We also considered 2-way interactions. So we looked at pairs of options to see whether that particular pair enabled some nonlinear increase compared to the options individually. And we also vary by benchmark program. So basically the idea here is to allow us to factor out differences. You know, if you analyze a program that's 1 million lines and a program that's 100,000 lines, no surprise that the one 1 million lines is going to take longer. Also, other features of the programs are going to matter. Treating each one of those programs as a separate configuration option and then ruling it out allows us to focus on the parts of the analysis, the performance or precision that are true across all of those programs. That's the idea. When producing the models, we used what's called the, I don't know how to pronounce that, AIC, to drop insignificant variables from the models. So instead of presenting a model that has however many independent variables that is, a lot, there's an iteration process that tries to find a good fit, and it drops parameters that seem not to affect the overall model by very much. So it's a way of sort of a pre-pass that identifies significance, and then there's a separate pass where we use p-values and such to determine significance in particular cases. And the models actually fit pretty well. So this R squared of 0.72 or 0.98 is pretty high. So frankly, I was a little surprised that it fit as well as it did. In the performance analysis, we set the timeouts to be 1 hour, as I mentioned. And so the question is, how in this analysis should you treat a timed out run? So for the performance, we treated the 1 hour, the timeout, as if it was 1 hour. So the function of performance for all the runs is then therefore a lower bound. Certainly the analysis might have run longer if we had allowed it to, but it's hard to know how much longer it might have run. So you should think of, if it looks like things are bad, according to our analysis, they could actually be much worse, because timeouts, if allowed to run longer, might have done much more. On the precision time, if we have a timeout, we just throw away that run. And what that means is that you'll just have less information about runs that timed out, configurations that timed out, and they won't contribute to the overall model by very much. And so therefore they'll have a lower p-value, and we won't treat them as significant. And I should say this is following the advice of Arcuri and Briand, who had a paper in XC11 that suggested taking this approach. In the paper, if you like, you can see a separate timeout analysis where we looked at what is the likelihood of the analysis to time out given particular programs and, particular analysis options. So here is a very interesting one. If you use access paths rather than summary objects, it reduces the likelihood of timeout by 40,000 times. So when we said that summary objects were slower than access paths, we really meant it. Okay, so now let's look at one of the models that was produced by this analysis. So I'm going to explain what this table means. So on the leftmost column is the analysis option category. So abstract object representation, heap abstraction, context sensitivity, analysis order is the first one, object representation, and then finally numeric domain at the bottom. The individual settings are there in the second column, top down, bottom up, and so on. The next number is the number of minutes that were contributed to the running time relative to the baseline. So each one of those options with the dash there is the default configuration, and then each one of those, the lines here, is the delta from that configuration, right? So what that's saying, for example, is for bottom up, if every other option in the configuration was the same, that is AP plus SO, one type, allo, and Paul, all of these baselines here, but we modified TD to instead be BU, that on average knocks 2 minutes off of the running time. Okay, so these are deltas against that baseline. The green rows are indicated as statistically significant, so they have this p-value that's less than 0.05. Finally, this column indicates the 95% confidence interval, so this is the sort of middle number, and here is the range that that number could take on with 95% confidence. So for this particular chart, we can see a couple of interesting trends. So first of all, the default was AP-SO. If I drop the SO part and just have AP, that knocks 37.5 minutes off of my analysis time. And remember, the running time on average, the maximum timeout was 60 minutes. So that's a significant performance improvement. Down here, we can see that intervals are also providing a significant performance improvement. But interestingly, they're not as bad as summary objects, right? So if we only looked at papers that said, oh, you should use polyhedra versus intervals, you might go, okay, yeah, I should do that. But when compared against other analysis trade-offs, like how you implement the heap, it might be that this difference is not so significant, and you're perfectly well justified in holding on to polyhedra by using access paths instead. In this case, if you use the context sensitivity or heavyweight object representation settings, that is the ones here at the top, allocation site, that's the most precise but most expensive. If you get rid of those, you save yourself in terms of performance. Interestingly, as I already sort of mentioned, the bottom-up analysis, even if you just look at that number there in the first, in the est number column, you don't see very much of a difference, and in fact, that difference is not statistically significant. And I think the reason for that is the top-down analysis already gets a lot of leverage from reusing these summaries, that every time you analyze the method, you get to reuse a summary a fair bit. Okay, so that's performance. Let's switch to precision. Here's our table here. It's the same format as before, but now the column that's indicated there is how many array bounds checks are proved correct by the analysis. So in this case, higher is better. So if I see a negative number there, what that means is that there are fewer array bounds checks that I could prove were reasonable. So here, we can see that access paths are critical to performance. That is, the baseline is AP plus SO. We would think of that as likely to be the most precise case. So if we get rid of access paths and just hold on to SO, that's what that row is doing, we lose 94 array bounds checks being valid. Bottom-up analysis harms precision overall. So you can see when we switch from top-down to include bottom-up, we lose a whole bunch of array bounds checks. And here, when bottom-up is combined with summary objects, that is summary objects not including access paths, that's sort of a double whammy, right? So basically those conditions that we just looked at added together are just catastrophically bad. Doing bottom-up with only summary objects kills you. The relational domain, convex polyhedra, improves precision. So when we switch from access paths, we switch from APSO pol to AP int or SO int, we're going to lose some checks. So polyhedra do improve your precision, as you might expect. And finally, the more precise abstract object representation does improve precision. So the allocation site is better than using the class-based one. But notice that context sensitivity doesn't even show up in this model. So the AIC criterion causes us to drop context sensitivity, and it ends up not helping out very much. Okay, so now I'm going to look at the trade-offs. So this giant table is showing for each program what the best and worst, the best performance and best precision configurations were. Right. So for example, here it's saying the best precision for LU search was top-down, access paths and summary objects, 1 CFA call site sensitivity, allocation site object-object representation, and polyhedra. And you can see that there's some trends here. So for example, the best precision almost always is top-down AP. Sometimes APSO is the best precision, and that's not surprising because APSO is the combination of those two. And the best performance is always including access paths. Summary objects are not there, and bottom-up is often a part of that. Here you can see there's actually sometimes a large range between the best and worst performance and precision. So on the best performance case, we have 0.3 minutes compared to 1.4 minutes. That's not very much of a difference, and we get a whole bunch more checks. Whereas here, we went from 1.8 minutes to 47 minutes, and to have correspondingly more checks. So the range of the two can be broad or small. Okay, so now I'm going to show you a few of these charts that try to show you the trade-off between precision and performance. So each dot is one configuration for one program, right? So this is for the Antler program, and there's 162 dots here, one for each configuration. The dots are grouped according to one of those configuration groups. So this is showing you whether to use access paths or summary objects as your heap abstraction, grouping all of the other things under the same picture. So the best case is the upper left. That's where you have the highest precision and the least performance. And the worst case is the lower right. And basically, these are all timeouts. So one trade-off is that access paths improve precision and have good performance, and summary objects slow it down and are imprecise. So you can see there in the upper left, we have APSO and AP all grouped together. We have AP all grouped together. We have AP all grouped together. And then down here, we have SO with terrible precision and moving to the right in terms of performance. And this should not be surprising given the two models that we saw. So top-down analysis also seems to be the winner if we want to both improve precision and not hurt performance very much. So you can see here, now the circles are bottom-up analysis, so that the bottom-up analysis, we can see the precision is very low and it's trending over to the right. whereas the top-down analysis, those red triangles, the precision is up higher, and we see this greater grouping to the left. Here's an interesting interaction. So access paths and polyhedra generally are better than access paths and intervals. That shouldn't be a surprise. We keep access paths the same, but we take the more precise convex polyhedra. So you can see the green ones are the polyhedra. This is two charts. The left-hand side is the heap abstraction. The right-hand side is the numeric domain. These are all the same points. We're just highlighting that grouping of points. So the same set of points in both graphs are AP and polyhedra versus AP and intervals. And you can see the AP ones are higher, so they are more precise. Sorry, the poly ones are higher, so they're more precise. Now on the flip side, APSO, which we know is going to be slower because we added summary objects, with int tends to be better than APSO plus poly. Why is that? Well, it turns out that APSO plus poly is going to more often push you over your timeout threshold so that you're going to end up with more stuff here in the lower right, and you're going to be able to decide more things when you include APSO and intervals versus APSO and polyhedra. And so that's showing this grouping up here. Okay, so in short, access paths, always a good idea. Summary objects and access paths do add precision, but summary objects are really slow. And so unless you're prepared to run for much longer, it's probably not worth it to include summary objects. Polyhedra improve precision, but they're going to time out when you have this APSO case. And top-down is more precise than bottom-up. Summarizing as far as this work itself, we spent all this time doing this analysis to try to look at the trade-offs for these different options, and then actually published our results rather than keeping it all to ourselves and just saying, here's a numeric analysis that you should use. I would suggest there should be more of this so that we can dig into that data. I'm sure you only got a flavor of it from my talk about what these different trade-offs are, but hopefully if you went and looked at the paper, it would illuminate a bit more about how you might build such an analysis yourself. And who knows, maybe this idea of using multiple linear regression is a good way of understanding this complex configuration space that you might consider as well. As a final comment, I just want to plug work that we have been working on in SIGPlan to come up with a checklist. This is the checklist for doing an empirical evaluation. It might help you in performing empirical work of your own to do work that is more likely to be not present misleading results. And it's set up as a checklist according to the checklist manifesto. So I'm happy to talk about any of the work that I just presented to you or this checklist if you have any questions about it.
All right, let's thank Mark. So I think we have a few minutes for some questions. Peter?
I can start. So that was a great talk. Thank you. So another trade-off that developers of static analysis often face is performance versus soundness, right? People, have unsound heap abstractions or ignore integer overflows or ignore exceptional control flow. So if you look into that aspect as well, and if not, could one use the same methodology and explore that?
We have not looked into it. That's a really good idea. I think the challenge there would be how to characterize precision. You'd have to start including ground truth. So basically what we've done here is we've assumed all those array bounds checks were actually in bounds. There weren't any bugs. That might be wrong. There might be bugs there. In the unsound analysis case, you would need to characterize that loss of soundness somehow, which we're factoring out in this particular case, right? So it may turn out that the unsound analysis, I'm able to prove all these checks are in bounds because I didn't flag them as possible bugs. But that may be wrong. It may be that it didn't flag it because it's using some approximation that's unsound. So you'd have to distinguish that between not flagging it for that reason and not flagging it as in the sound case because you actually know that there's not a problem there. And that would require you to know what ground truth is. But otherwise, I think you could use the same methodology.
Okay, thanks.
Other questions? Mike? Oh.
It seemed like you were using
about ground truth,
most precise analysis as a proxy for ground truth. Was it the case that the less precise analyses would at least agree with the most precise one on the checks that on the ones that they both the indices, the accesses that they both deemed were secure?
That's a great question. Right, so just to be clear, the baseline that we use in those tables is just, this is the way multiple linear regression works. You have a baseline and then the models are deltas to the baseline. But your question is a valid one. When all of those configurations complained, and one was less precise than another one, did they complain about the same things? Was it sort of a subset relationship? And I mean, not always. So it may be that different trade-offs cause you to have false, basically we think of all these things as false alarms, right? So in that table where I showed the DaCapo ones, I showed the total count of checks. So all of the checks that I'm not able to discharge for a particular thing, I'm assuming are false alarms. I'm assuming the complaint is wrong. And so they will complain about potentially different things depending on which analysis options you have in play. If it turned out that some of those were really bugs, then I could answer your question. But I don't know if any of them are really bugs. I just assume there's no bugs in the programs.
Okay, so if you folks have any other questions, please feel free to talk to Mike afterward. So let's thank Mike again for the nice talk.